I know that now things can go well without me last week.
They didn't post a photo, right?
Yeah, everything was fine.
We needed more than one person to replace you.
Huh?
We needed more than one person to replace you.
I mean, that's not surprising.
Can I write my name?
No.
Everybody knows you're working. All right. So thanks for coming. So we're pleased to have Laure from Montpellier. So please, you will tell us something like to modify quickly, right?
Yeah.
All right.
So hello everyone. So this is a talk about graph modification problems where the modification involves a bounding number of vertices. And this is a work I did with my PhD advisors, Ignatius and Dimitrios Tilikos in Montpellier. So first, what is a graph modification problem? So you have some kind of modification that you fix. You have some kind of target class H. And the question is, given a graph G and an integer K, can I do at most K of this modification so that the modified graph belongs to my target class H? So a lot of problems can be written like this. For instance, if your modification is vertex deletion and your target class is edgeless graphs, then this is vertex cover. If your target class is forest, it is feedback vertex set, and so on. And you can even do some kind of modification where you say, okay, the modification I'm allowed are adding edges and removing edges, so you can mix several of them, and still this is a modification problem. So for instance, if you can add and remove edges and your target class are union of clicks, this is cluster editing. So you can take any kind of modification you want, any target class, and this gives a new problem. However, most of the graph modification problems are NP-complete, and that's why usually we study them from the parameterized complexity point of view. So essentially, we will fix the solution size K, so the number of modifications we want to do, and we try to find some algorithm with running time that is some function of K times some polynomial in N. So this is what we call a FPT algorithm. And well, a lot of people worked on graph modification problems. I didn't find a survey on all graph modification problems, but just for those that involve edges, you have almost 300 papers in just one survey. And I'm pretty sure there are more papers just on vertex deletion, for instance. So that's why you can ask this question. So instead of trying every problem separately to solve them, can you just not do a meta theorem that says for every target class that has these properties, or for every modification that looks like this, then I have an FPT algorithm with the running times that I want. So there are some results like this, for instance, where you fix your modification, but you find a result that works for a lot of target classes. So in particular, I will talk about minor classes. So H is a minor of G if it can be obtained by removing edges, removing vertices, and contracting edges. And a minor cross graph class H is a graph class where if G belongs to this graph class, then all of its minors also belong to the graph class. And we have a lot of nice results on this. So a lot of graph classes can be expressed like this. So edgeless graphs, forests, planar graphs, and so on and so on. So we have a lot of nice properties on minor cross graph class, and in particular, we know that the minor cross graph class has a finite number of obstructions. So an obstruction is a graph that does not belong to the graph class H, but such that all of its minors belong to the graph class. So for planar graphs, it's K5 and K33. And actually, we know that checking whether some graph is a minor of your input graph is polynomial. So here I just put the last results on the subject where they say that you can do this is almost linear time. And from these two results, actually, you can check that checking whether a graph belongs to some graph class H can be done in polynomial time. So why? Because you can just, for each obstruction of your graph class, check whether it's a minor of your input graph. If yes, then you say, no, it doesn't belong to the graph class, otherwise it does. So that's why we can check whether we belong to a minor class graph class in this running time. And this in particular means that already we have some graph modification problems that can be solved in FPT time. So in particular, this is the case for vertex deletion and edge deletion. So why is that? It's because, for instance, if you take vertex deletion, the yes instance of K vertex deletion form a minor cross graph class. So that's why we can just check whether we belong to this minor cross graph class or not in polynomial time, and we solve the problem. However, this does not work for every graph modification problems. For instance, if you want to contract edges, this is not a minor cross graph class. So this does not work. So we saw a meta theorem on target classes. Now we can look at some theorem on modifications. And the first question is how to generalize several modification problems and to speak about all of them at once. So for this, for instance, we can use replacement actions. So replacement action is a function that maps a graph H to a collection of graphs of same size. And essentially, this replacement action will describe the modification that you are allowed to do. So for instance, if the modification you want is removing K edges, for to each graph H, you will map all the graphs that you can do from H by removing at most K edges. And this way, so we have a problem that will help us represent a lot of graph modification problems. So this is L replacement to H. So you have a graph T and an integer K as an input, and you ask, can I find an induced subgraph at size at most K in my graph, T, such that if I replacing with one of the graphs that are in L of my induced subgraph, so one of the allowed modification, then I get a graph that is in my target class. So this problem, it was proven that when your target class is planar graphs, then this is FPT. And in particular, for several problems, for several graph modification problems, this gives you the same running time. So for instance, this replacement action can, like I said, can represent edge deletion. You can also ask whether you can remove a matching of size at most K such that your graph is planar. You can also ask whether it is possible to take a subgraph, replace it by its complement so that it has your graph at some properties after. And you can even do some stuff that don't look like graph modification problems. So for instance, planar subgraph isomorphism. So is there inside my graph a subgraph that corresponds to some graph H that is planar? So this is nice to represent a lot of problems, but here you can see that it's only problems where you add and remove edges. With this kind of way of doing, you cannot remove vertices or this kind of stuff. And then there are super powerful meta theorems that are both on modification and target classes. So in particular, we have this result that I will not explain, but that says the following. So most graph modification problems where the target class is minor closed and where the modification involves only a vertex set of bounded annotated truths can be solved in NFPT time. So first, what is a truth? So a tree decomposition of your graph G is a tree where you map to each node of your tree a bag of vertices of the graph, such that each edge is inside the bag, and if you have a vertex, for each vertex, the bags in which it is are connected. And so the truth is the minimum if your graph has truths at mathcal, if you can find such a decomposition where each bag has size at mathcal. So for instance, trees have tree width 1 and grids are have big tree width. And the annotated tree width, well, I will explain just for fun, but you can just not care because we will not really use it, is like almost like the true width, but you add the set x that is in your graph. And you will, so the annotated tree width of g on x is the maximum tree width of an x minor g. So what does it mean? If I have this set x in my graph that is the grid, then I look at all the minors I can do where each bag that I contract contains a vertex of x. And I look at the tree widths of all such minors, and here, for instance, I have this grid that appears. So if this is size k, then this is a grid of size k, and so this has tree widths, annotated tree width k. But if I look at this set of vertices, then I cannot do a big grid. At most, I have a square. So that's why the true width is always 2.
So when you say x minor, so here x is a set of vertices, or
X is a set of vertices
the
of your
blue-
graph.
the blue-
Yeah, the blue vertices here. And so next minor is, you look at the model of your minor. So you have the bags that you will contract together, and each bag should contract a vertex of x.
I see. So you wanna build a minor on x.
Yes.
Okay.
Oh, I'm going to. Okay. So in particular, in our case, we want to look at modification where the vertex set that is involved in the modification has bounded size. So if it has bounded true width, annotated true width, that's already bounded size. So this is more powerful than what we will try to do after. Okay, so this is a super powerful result, and somehow it seems like everything is done, right? Most graph modification problems can be written like this, and so if your target class is minor closed, somehow you just know it's FET and that's all. But still there is one problem, which is this f of k. Because what is this f of k? So this parametric dependence, we don't really know it, but just it's bad. So that's why we don't know it. And so our goal here is to improve the parametric dependence in K.
What does very bad mean?
Well, first, a lot of stuff are hidden in the Coursera theorems that everyone uses. Plus, you use the unique linkage theorems that I didn't check, but I don't know. I mean, there is a lot of tower of exponential and this kind of stuff.
So some tower that depends on the k.
Yes. 2 to the 2 to the 2 to the 2 to the something.
Not
Okay.
really, I think.
No.
So
Not really?
Cosell depends, this high depends on
Coursera is
style,
alright,
right?
but there is other stuff that we use, and I think it's bigger.
The at least
So
unique
linkage
linkage is like quadruple exponential.
Okay,
Yeah,
so
it's
maybe
fixed.
maybe
It's
maybe
a large
it's
large
bigger
tower,
now.
but it's fixed.
The tower of bounded height.
Yeah.
Yes.
Yes.
So you so I have difficulty understanding the meaning of vertex set of annotated tree with k. So do you have
So
some example where certain problem, you can use this.
Okay, so for instance, if you want to do elimination distance to H, so essentially the vertex set that you will remove. Okay, here it has bounded through it. It's wait, okay. So here you could just do through it instead of annotated through it, and most problem I know can be say like this. So elimination distance to H. Here you do you see what it is? You remove a vertex from each step. You remove a vertex from each connected component, and so that your graph at the end belongs. Each connected component at the end belongs to H, and the depth is the number of steps that you did.
Okay.
And essentially, the number of vertices that you removed has bounded 3 depths, and so bounded through it.
I see.
And there is also like the H3 width. Here you want to find some kind of tree decomposition where the leaves belongs to H somehow. It's not exactly this, but almost. So again, you want to remove a set of bounded through it. So trying to improve this parametric dependence is the result of a long series of papers and of PhD students, because you can see that there are 2 authors in common in each of them. So first, after 4 papers, it was proven for vertex deletion to H that we have this running time parameterized by the tree width. Then, after 2 papers, we had vertex deletion to H and this running time parameterized by K.
So sorry, the first one, is it the tree width of the entire graph or of?
Of the input graph.
Okay.
Then we managed to go from n cubed to n squared, and now we did many modifications. So essentially the L replacement that I talked about to H is in this running time. So each time we improve the previous results. So what is exactly the statement that we prove? So like I said before, the L replacement, so here you have a replacement action that maps the graph to the modification somehow that you're allowed to do. But here, like I was saying, the problem is that with the setting, you just map a graph H to graphs of the same size. So somehow you explain how you add and remove edges, which is not enough, for instance, if we want to do vertex deletion. So now, instead, we can map to a collection of graphs of smaller size. And here, however, it means that we need to know how the graph of H are mapped to the graph of F. So that's why we add some function that says, here also represented by the colors, that says for each vertex of H where it is mapped. So I just put the color. So for instance, you can have edges that are identified if phi maps them to the same point, and some of them can be deleted. And so our question now is, like this. So you either set S again, where I look at the induced subgraph and can I remove it, replace it by another graph that is an L of H, such that my graph belongs to H. So here, however, I was cheating a little bit because we have a new constraint. We ask that our replacement action is what we call hereditary. So what it means is that, for instance, if your graph H can be modified to this graph F, then if you take a subgraph of H, you can modify it to the subgraph of F. So if this is an allowed modification, then this one should also be one. Essentially what it means is that you can ask, can I remove at most k vertices, but you cannot ask, can I remove exactly k vertices. So here is a list of problems that we can solve with this statement. So you can do vertex deletion, edge contraction. You can take a subgraph and take the complement of this subgraph. You can identify vertices, you can contract a matching, you can remove an independent set, and so on and so on. So you can do a lot of stuff, yes.
How do you use this LIRMM replacement to do vertex identification?
Identification, so let's say this identification, there are several ways to define identification, but let's say you say, can I identify k pairs of vertices? So here essentially, you ask, your allowed modification is for each graph H, you find all ways of identifying k pairs of vertices together, but for the problems that you ask, instead of saying, can I find a set of size k such that I do the modification, you say, take a set of size 2k. So somehow, if there is a way to identify k vertices, then there should be 2k vertices that are involved in your modification. So you take the subgraph, induced subgraphs that correspond to these 2k vertices that will be identified, and you do the identification here. Is this clear?
No.
Okay.
I'm wondering because if I just want to identify two vertices and then they would have the same neighbors, right? Or rather, their neighborhoods would be the union of their previous neighborhoods.
Oh, you mean like this? Let's go back. Okay, so here I can identify two vertices if phi maps these two reds
So I
to
just
the same
label them
one.
the same and then.
Yeah,
okay.
and then the neighborhood is just the union of the neighborhoods.
Okay.
of the two.
So it's like a contraction.
Yes, it's like a contraction.
In one of in the next page, one of the problem is subgraph complementation.
Yeah.
Do you allow arbitrarily large subgraph to be complemented?
No, I ask, can I find a set of size at most k, so that I take the complement of
I see.
this. And so there are some problems that we cannot do because you cannot, they are not hereditary. So like I said, you cannot exactly remove k vertices or k edges. It must be at most, but this is alright because somehow usually you want to minimize the modification. And also I was saying before that we could do planar subgraph isomorphism. It doesn't work anymore in this setting. So here is, can I take H that is planar, and the question is H a subgraph of my graph? So it worked before, and here it doesn't work.
But these problems work in this big meta field with the vertical, right?
Yes.
Hmm.
I think so. Yeah, they do.
Good. Is that what you mean is like you ask for k and then you ask for k minus 1?
Oh no, I just wanted to if
In the
Yes.
big meta theorem with annotated through it, he was
Yeah.
asking if all of this worked. And yes, I think all of
so
this.
if I really need to solve this, I can sacrifice my running time to
Yes.
go there. But
Yeah.
if I want to be quick, then
Yeah.
I
Yeah,
have
but
to be.
for instance, deleting exactly k what this is, I was thinking that just first ask for k and most k and then ask for most
True.
k minus 1.
Ah, true. Yes.
True. This
Maybe
would
this
work.
gives you
Yes.
compliments.
Huh?
If both answer yes, how does that help?
If both answers yes, then okay.
Yes.
Alright.
So can you remind me what is the planar subgraph isomorphism?
You take H, that is a planar graph, and the question is H a subgraph of your input graph?
Okay, a specific H. Okay, thank you.
Okay, so this is what we can do. So in all the meta theorem I presented before, essentially they all use the same technique, which is the irrelevant vertex technique. So this is a technique that originates from Robertson and Seymour. And for what I'm interested in, there is a version that works with minor cross-graph classes that was used for vertex deletion. And then we improved this to do it for any L replacement problem. So essentially, what does this technique says? So you take a wall in your graph. So a wall is a graph that looks like a wall. So also it's an hexagonal grid. And more than this, actually, we want a flat
This looks like a
So right, you still have a wall inside, but you have more structure around. I will not explain this, but this is one of the reasons most papers on minor graph classes begins with 10 pages of definition. And essentially what you can say is that if you find a flat wall in your graph, then there is a vertex, you can find a vertex in this flat wall that is irrelevant, which means that if gk is a yes instance, if and only if g minus vk is a yes instance. So if you find such a vertex v, you can just remove it and recurse again and again, which is nice. So the question is how to find such a flat wall. Yeah, sorry. First, actually what we will usually find is a set A that we call an apex set, such that if you remove it, you have a flat wall in your graph. And so we have some version of the relevant vertex technique that says, okay, if you find this structure in your graph, then you can find an irrelevant vertex in the running time that is above. And what is important is that this running time depends on the size of the apex set by a function that is bad. So I will try to not have k in this apex set because it will be very bad after. Okay, and to find such a flat wall, there is something called the flat wall theorem that also originates from Robertson and Seymour, but there are a lot of different versions depending on what you want to do. And essentially what it says is that in a graph, given a graph G, either this graph contains a big clique as a minor, or it has bounded through it, or there is a set, an apex set A, such that if you remove it, you have a flat wall in your graph. So in the last case, we can use our irrelevant vertex technique, which is nice. And so you find an irrelevant vertex V, and you recurse on G minus V. If you find that G has bounded through it, then usually most people use Courcell's theorem that says essentially that most problems you can solve them in linear time parameterized by the through-width. And in this case, I can just conclude. And so now, if I have a big clique in my graph, so I will be able to say that this is a no answer. So why is this? It's because if you take an obstruction in your graph, and you take this the size of this obstruction plus k, no matter how you modify k vertices in your clique, you still have this obstruction. So you can say no. Okay, we have this, which is nice. However, there are some problems, which is that t depends on k, and because of this, here we have two running times that depends on some function of k that I don't know. So we will try to solve these problems. And first, we will look at the Courcell's theorem. So we cannot use this theorem if we want to optimize as much as we want the parametric dependence in k. And so instead, we will do dynamic programming. And I believe this is the reason most people don't try to do optimization of graph modification problems, because they just don't want to do the dynamic program.
Yes.
So I will just first explain for vertex deletion, because it will help us for the general case. So here we use a representative-based technique, which says that essentially if you have a graph G with some boundary, some vertex B, vertex at B, which is on some kind of boundary, then you can find a representative of this graph G of small size, such that no matter how you grow a graph on the other side of H, this graph belongs to, yeah, I don't know how to use a pointer. The first graph belongs to H if and only if the second graph belongs to H. And so how do you use this? So if you have your tree decomposition, so we go from the leaves to the root, and each time in a bag, so you guess the intersection of the solution with the bag. So you remove it and the rest should belong to H if it's indeed some part of the solution. So we do this kind of guess. We did it for every leaf. And then for the parent, again, you guess the intersection with the solution, you remove it, and you need to check that what is below belongs to H. So this should belong to H. But somehow, this way of doing each time guessing the solution, the information that you need to keep when you go above is what is your guess on the solution, and you also need to keep as an information what is below so that you can check that you are still in H. The problem is that keeping everything that is below is too big, and that's why you can just keep the representative of your whatever is below, because no matter what happens above, if you have something in H, it was already in H with the other graph. And so essentially, the signature of each vertex of the tree, each node of the tree, will be just the intersection of the solution you guessed with the current bag and the representative below. And so the number of representative is bounded, the guess on the solution is also bounded, so the size of the signature is bounded, yes.
How do you find this representative?
There is a way to find. So we know that there is a bounded number of representative. Well, I wrote. I forgot right now, but 3 years ago I wrote how to find this.
So you do it by hand. You don't just box it somewhere.
So you know the maximum size of a representative. So it's linear in the true width, I think. I mean, I wrote it just before.
Yeah.
So it has bounded size. So you can just try everything to see who are the representative. So it's some kind of preliminaries before pre-processing. You find the representative, you do some stuff with matrices, and it works.
It's linear, but there's some factor depending horribly on H, I guess.
I guess. And so if you compute this signature at each node and you arrive at the root and your signature is not empty, it means that you found a set S such that if you're removing it, your entire graph is in H, and so you are happy. And so essentially the size of the number of different signatures will correspond to the parametric dependence we have above for the true width. Okay, so this is for vertex deletion, and now for L replacement we will do something a bit similar. So again, you go from the leaf to the root, you guess the intersection of your modified vertices with the bag, and you also guess, you guess this. But here now you need to be careful. Like before, you guess what vertices would be removed and you just remove them. Here, it might be that you want to identify a vertex somewhere, like in a leaf with a vertex in another leaf far away. So somehow you need to keep in mind the information of the partial solution. So like you need to have some bag that contains both U and V. And so to remember U and V everywhere before. So here essentially, okay, I guess the vertices that will be involved in the solution, and I also guess what kind of modification I do on these vertices. And so after doing this modification, I should have a graph in H, and I, like before where I remove the vertices that should be deleted, here I do the modification that I can, that I guessed, so that whatever is left belongs to H. So you do the same for every leaf, and then when you arrive at the parent, I guess you guess the intersection with the solution, and you guess how it will be modified, And essentially it needs to be an extension of whatever guess you had just before. Like you take your guess you had for the children and you extend it to the new vertices that you imagine you guessed to be in the solution.
So you need this hereditary property?
No. Well, I could use it, it's easier, but I think even if not, you can somehow change the replacement action you take at the beginning so that now you have something that will work. I mean, hereditary is mainly used in the irrelevant vertex technique. And so you replace by your guess on the modification, and again, we will take the representative instead below so that you have something that is in age below that is not too big. And here you see, I remember, essentially I remember the modified part, and I remember what was the graph that gave this modified part, so that I can check that each time when I decide some kind of modification, it's a modification that is allowed. Okay, and the signature, so it's the subgraph that I modified, the subgraph that I get after doing the modification, and the representative. And again, we can prove that this is bounded, and this is a yes instant if and only if the signature on the root is non-empty. And so this gives this running time above. So here it depends on k, and we don't know how to remove this parametric dependence in k. So even if you use Courcell's theorem, actually, the way you write the formula depends on k. Okay, so we had this, and now we don't use Courcell's theorem anymore. We have something with some kind of nice function in k, so it's alright. And now we need to take care of the irrelevant vertex technique.
So sorry, just for that. Is it true that if instead of some h which is minor clause, I give you I don't know any three automata, and I ask you if you can do replacement to that automata?
This is from my closed graph classes.
Yes, but okay. I get the impression that it's you.
So
there are two independent parts. There's one which is for minor closed classes. You have you can do it with a correct complexity, and then if you want to do replacement, that only adds 2 to the polynomial overhead.
Sorry, say again. I interrupted you,
So I get the impression that your proof has already 2 parts, which is you have testing if you are in H in the complexity you want, and then you add the replacement part, the modification, and this doesn't add too much. This only adds 2 to the polynomial.
Yes.
I mean, multiply that. So I was wondering if you could replace minor by just any problem which you know you can do the correct complexity and you would still get the same result.
So I'm not sure I understood, but just to say, I'm not sure it will answer to your question or not, but the representative-based technique only works for minor closed graph classes. So the technique that I used works for minor closed graph classes only.
Okay. Okay, then I'm quite cognizant of
It's because you somehow use the Robertson-Zimmer theorem, like you use some.
So I use it black box personally.
Yeah.
So
Okay.
I don't know, I don't remember how they did, but yeah, surely something like this. So now to take care of the irrelevant vertex technique. So the problem, if we remember, is that the apex set is too big, it depends on k, and that's why the irrelevant vertex technique has some bad function in k. So we will do branching. So what will we do exactly? So you take an obstruction of your graph class, and actually you can see it as a planar graph plus some set above. The apex number of a graph is the smallest number of vertices you can remove so that the rest of your graph is planar. So you can have a set of size apex number above and a planar graph below. And AH, it will be the minimum apex number of some obstruction in H. So essentially, you can find a graph F, an obstruction F, that is just AH apices above and a planar graph below. So for instance, for planar graphs, this apex number is just 1. So you have this kind of stuff in in obstruction. There is an obstruction that looks like this. And here what you can see is that any planar graph is a minor of a big enough grid. And so the first graph is this obstruction. You can find it in this graph that is composed of your apex set of size AH and a big grid below and all the edges between the apex set and the grid. And if you have k plus 1 such grid, no matter how you choose k vertices that will be involved in the modification, there is one grid that is free from any modification. So this means that here we have F as a minor, unless there is a modification that is done in your apex set A. So essentially, if you find the structure in your graph, you know that some modification is done in this set A of small size. So here I just put all the grids together to just say, okay, if I have a big enough grid, if I find a big enough grid and a set above that sees everyone, that I know that I need to do some modification in the set above. Okay, so now that we have this, let's see again how it works. So we have the flat wall theorem that says either we have a big clique and then we say no, or we have bounded through it and we conclude, or we find a set A such that if you remove it, you have a flat wall. And then we have two cases. So either there is a lot of flow between A and your wall, and then you can contract the wall such that you will find this as a minor, so a big grid and A above that sees everyone. So this means that, well, for some A primes of size AH. So this means that you can just guess what is the modification that is done in this A prime. And we will branch on this case. So essentially, okay, you guess the vertices involved in the modification and you guess the modifications that you do. And that's why in the input, actually, you don't have just G and K. You need also to remember some vertices that are already, that will be modified and what kind of modification we do on these vertices. And so we recurse on the new modification that we guessed. That's what was below. So this is not a big search tree because we know that at most k vertices are involved in the modification, so it has depth at most k. And your set A prime says at most the apex number, so it's not too big. I mean, it depends on age. And now the third case is if there is a small flow from your apex set to the wall, then you can find a smaller wall in size that sees only vertices that sees at most AH minus 1 vertices above. So this does not depend on K, which is nice because now we can use the irrelevant vertex technique, and you don't have a K that is at somewhere we don't want it to be. So this is nice. This seems to give what we want. However, the running time actually is bigger than what we really want because I claim that we can do in 2 to the poly k time n, and here you can at least a double tower of exponential. So that's why at least here I presented all the arguments that we use, but actually the way you do the algorithm is far more convoluted than this. So I will not explain in details, but I will just show quickly how the real algorithm works. So you have your input, so G, K, and the modification that you guessed for now. And now we have an algorithm that says either this is a no instance, or this has bounded through it, and we can conclude. Or you find a big wall. So here we don't find a big flat wall, just a big wall, which is less expensive for the running time. And you look at each sub-wall of your big wall that is big enough, and essentially you will search whether this corresponds to some flat wall. So if there is an apex that you can remove so that it is a flat wall. So actually for this we use two different versions of the flat wall theorem, and well, it's complicated to find correctly. But anyway, if you find this, then you can use the relevant vertex technique and recurse on T minus B. If not, then you look at every vertex of your graph that is not in the wall, and you will look at whether it has a big flow to the wall. So all the vertices with a big flow, we will put it in a set B. And for every subset of B prime of B of size AH, we will do the following. So here you see that I made some green bags, so that if you contract the green bags inside, essentially you have a grid. So I will just greedily extend, as long as there is a vertex that is not in a bag and that is adjacent to the bag, I will add it to this bag greedily. So I do this, so for all vertices of G minus B prime. And now, if every vertex in B prime is adjacent to enough bags of enough green bags, then actually I can just contract the green bags and I will find this. Well, maybe some edges will be absent, but you can argue after that you can find what you want. So this means that B prime should intersect the solution. So again, you branch, you guess what is the intersection of the solution with B prime and what modification you do there, which is alright. And otherwise, you say no. And so one of the most difficult parts of the algorithm is to argue that you can say no if you didn't find, if you didn't branch or if you didn't find an irrelevant vertex before. Okay, so with this, we get our running time. So there is still a question, which is, what is this polynomial in K? So actually, I don't know what it is, but it's bigger than this. Which means that even for planar graphs, this is too big for my calculator to compute. But at least for the case of planar graphs, we managed to get K to the 10 instead, which is better. And so why is that? So it's caused by the irrelevant vertex technique. Because essentially, in the general case, you have a flat wall, and what you really do is you find something called an homogeneous wall inside, and you can argue that the central vertex of this homogeneous wall is irrelevant. And the size of the flat wall you need to find an homogeneous wall is this polynomial in K. And we have some examples that show that you cannot do better with this technique. And in the case of in the planar case, actually, if you manage to find a planar flat wall, then you can prove that this flat wall is already homogeneous. So you just take the central vertex and that's all. So that's why we don't have this polynomial in K. So, okay, these are the two results we found. So of course there are still open questions, like can we improve the running time? So this polynomial in K, I said it comes from the relevant vertex technique, so if you want to improve it, you need to find another technique instead. There is also the question for the n squared, because now we know that we can check minor membership in almost linear time, so maybe we could improve this to almost linear time. The problem is that the way they do is just to put everything in the Courcelle theorem. So if we wanted to do something, we would have to do a neural dynamic programming to solve this, which I guess nobody wants to do. And also there is this K to the 10, so maybe we can improve it. I don't believe we can do better than K to the 2, but we didn't really try to improve it much. So also, can we do more than minor cross-graph class? So maybe some of you work on odd minors. So we try to do vertex deletion to odd minor cross-graph class. The problem is that a lot of techniques are missing for now. Like we don't really know how to do the irrelevant vertex technique with parity for now. And also, can we remove the heredity? So this maybe, actually, like I was saying, it depends on it's used in the relevant vertex technique. So if we change this, maybe we can remove it, or maybe there is a way to not use it. But somehow, most graph modification problems, at least the natural one, we don't care about this heredity, so it's alright. Also, here I take as a parameter k, that is the number of vertices involved in the modification. But if you want to do elimination distance or H3 width, then this doesn't work here. So can we go further than this? So actually, the irrelevant vertex technique works up to annotated 3 widths, bounded annotated 3 widths, so it would still work. But the branching doesn't work because in what we did, it worked because each time you remove, you know that the depth is bounded by the number of vertices modified, but here the number of vertices is unbounded, so we cannot use this. Okay, so that's all. Thanks for your attention.
Thank you. Any questions?
I have a small question. At some point you said that you explained how you use KT as an obstruction in your algorithm, but for some KT is not a reasonable obstruction. For example, you had a modification to CLE, something like this?
This is not a minor cross-graph class.
Oh, so this is a different.
Okay.
Okay.
At first, you mean cluster edition, right?
Yeah, cluster.
So clusters are not minor cross, so
Okay.
it doesn't work. Essentially, here it's ready for minor cross-graph class, so you have some kind of obstruction.
So for all of your problems, KT has to be a reasonable obstruction for anything to work.
Well, it's work for any minor cross-graph class. You just take some obstruction in your graph class, of your graph class. Like, if you do planar graphs, let's take K5. So, if you find a clique of size K plus 5, no matter how you modify K of these vertices, you still have 5 vertices that are not touched. So you have a K5 here, and so you are not planar.
Yes, I was thinking of something like maybe there's a type of subgraph that is sparse and you would have to delete from the clique to actually get there, and this would actually go into the things you have to pay. But I'm just wondering if the only problems for which this works are ones where KT actually does form an obstruction without having to edit it further.
I don't know.
So if you replace size by H3 width, this somehow means that every tangle can only control a small size of the part that plays a role in your modification. So somehow it seems to me that if you, for a fixed tangle, if you look at the flat walls controlled by this tangle, you should still be able to do all of this irrelevant vertex stuff.
Irrelevant vertex works.
Yeah.
The problem is the branching.
So if you really want to be fast.
Yeah,
this is
so
quite
actually
good
we already have a paper on elimination distance.
stuff. Yeah.
The problem is that we cannot use branching, and so instead of a single exponential, you have, in the general case, triple exponential, and you can go to double exponential if you are apex minor free.
Nice. I mean, it's still better than
Yeah,
whatever
yeah.
the meta theory in this, but
Well, all the the very big meta theorem, it just use the relevant vertex technique, and they managed to use it in a very general form so that it works everywhere.
Do you know how this encoding for planar subgraph isomorphism works? Like, how do you make this into
Yes, so for any subgraph, if it okay, so when you look at your replacement action, for each graph, if it contains H as a subgraph, then you, let's say you remove it. And otherwise you don't do anything. And at the end, if the size of your graph changed, it means that you found as a subgraph your graph H.
Mm. So you just have in your replacements, you remember, okay, these are all the ways I could potentially create
just
this.
as long
and I
as
just
in the
delete it.
replacement somewhere you are allowed to do, I mean, just a replacement check whether there is H as a subgraph.
But so there isn't really a target class in that case.
Well, you could say just all the graphs with less vertices. No, wait.
No, that doesn't work, right?
So the way they explain in the paper, they just explain the replacement, and they said if there is H, you say yes. If not, and if for any graph that is you don't, you say no. Somehow they just say yes or no, and it's alright. I'm not sure what target class you're supposed to take so that it works.
Yeah.
I need to check. I will look again at the paper.
Thank you.
Are there any potential direction for clickers?
I don't know much about click so I cannot say. For click I'm not sure. I don't know enough about click to tell you this.
Any other questions? So if not, let's thank the